Hey guys, how you doing? Welcome to Coach Scott's Chemistry. We're going to talk about the nucleus for just a minute, right? And this is what we're going to cover next. Yeah. Once it was determined that atoms are made up of negatively and positively charged particles, J.J. Thomson and team proposed that the structure of an atom resembled what he called a plum pudding or a chocolate chip cookie, is what I like to think about it, right? So the model featured a positive sphere of matter, okay, big positive thing, sort of like a cookie, and inside of these little chocolate chip were these little chocolate chip negative particles called the electrons, right? So this is based on the idea that positive and negative charges attract and like charges repel. So, as we talked in our first week, models are always being continuously tested, and the search was on to find evidence to support the plum pudding model. So Ernest Rutherford, one of the students of J.J. Thomson, he used radioactivity to test this material, or this model. So what is radioactivity? It's the spontaneous emission of energy or radiation by an atom. So Rutherford studied emissions from the unstable element uranium. So larger elements like uranium they're pretty big, right? So they've got an atomic nucleus that's either stable and does not change, or it's radioactive, meaning that it decays or transforms over time into another element after a certain period of time. So decay can be short, it can be the fraction of a second, or it can be as long as a few million years. So what radioactive decay is the nucleus breaks into smaller nuclei and releases energy. So the three types of radiation were discovered by Ernest Rutherford. Okay, he discovered what he called alpha particles or alpha rays. These were positively charged particles that had a mass that was roughly 4 times that of the proton. Then he had beta rays or beta particles. Now these were determined to be electrons. And then gamma rays, and all those are is a form of high energy light. So what he was going to do was going to emit these particles in this lead block. So he put some uranium in there, some radioactive uranium, and this shot these rays through this gold foil. And then it went through these electrically charged plates, so you can see that alpha rays were a little heavier, so they were a little slower. Gamma rays were very fast, and there was no charge to them. Beta rays were attracted to the positive plate. So, which are particles? Well, alpha rays and beta rays. What we determined those were. So beta rays are attracted to the positively charged plate, indicating that they are negatively charged or they are electrons. Alpha particles are positively charged. So this is the gold foil experiment that Rutherford did, and this is a very famous experiment. You will see this for the rest of your scientific chemistry career. So Geiger and Marsden, they worked for Ernest Rutherford. They were postdocs. So what they did is they shot a beam of alpha particles at a thin sheet of gold foil. And then they observed the scatter patterns of the particles. Now their hypothesis was, okay, that these particles would go right through the sheet and maybe deflect a little bit whenever they hit one of the little positively charged protons. Oh, got to put my cursor in the right spot. So in the plum pudding model, or the chocolate chip cookie of the atom, the positive and negative charges were dispersed evenly throughout the atom, right? So if this was correct, these alpha particles, the high energy alpha particles, would be slightly deflected. They go back and forth, but they pretty much go right through the foil in a straight line. Now, what happened surprised everybody. So most of the particles went right through the foil, and there was no deflection at all. They were expecting a little bit more deflection than what they got. But what was really amazing is every so often, most of them went through, every so often, one would bounce right back at them. This was totally unexpected. Okay, so what did this indicate about the locations of protons in the atom? That they were packed closely and tightly together. All right, let's see what they say. The protons are clustered in the center of the atom. So these positive charges are all packed together. That should not be according to the plum pudding model. So the only way to account for those large angles, all right, was that all these positive charges were in a very tiny volume. All right, so a small dense nucleus must lie in a mostly empty atom. Now we know that the radius of the nucleus is only 1/10,000th that of the radius of the actual atom. So most of these charges went right through. Every now and then, this alpha particle would come around and it would be deflected by one of the positive charges. And yeah. So this is what Rutherford said. I remember 2 or 3 days later, the Geiger coming to me in a great excitement saying, we've been able to get some of the alpha particles coming backwards. Totally against the hypothesis of the experiment. So this was such an incredible event that ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell, a 15-inch battleship round at a piece of tissue paper and it came back and hit you. That's how unexpected it was. So this is a pretty huge experiment in the study of the atom. So it did what? Led to the discovery of the atomic nucleus? Yes. A is correct. The heavy subatomic particles reside in the nucleus. Now, electrons, because we measured them with the charge to mass ratio, we know they're so much smaller than protons. So Rutherford believed that the mass of an atom would be simply related to the number of protons present. That would make sense. However, they found that atoms were heavier than predicted because they were able to measure the mass. It's like helium. Helium has 2 protons and 2 electrons. So the mass you would expect it would be 2 times the mass of the proton. Actually, it's 4 times the mass of a proton. So maybe there is another particle. So Rutherford guessed it, and he came up with another particle he called a neutron, and he verified its existence. So neutrons have a mass that is pretty much the same as a proton, and there is no charge. So we use atomic mass units, or U, to describe the mass of a proton, or a neutron. So 1 AMU is equal to 1.66053892, whatever, 1.66 times 10 to the minus 27th kilogram. So a proton has a charge of plus 1.6 times 10 to the minus 19th coulombs. The electron is minus 1.6 times 10 to the minus 19th coulombs. No charge for the neutron. The mass of a proton is considered to be 1.0073 AMU, or exactly 1.6726 times 10 to the minus 27th kilograms. A neutron's mass is 1.6749, so it's slightly heavier than a proton, times 10 to the minus 27 kilograms, or 1.087 AMU. The electron is 9.1 times 10 to the minus 31st kilogram, or 0.00055 AMU. You can see it's much smaller. It has much less mass than the proton or the neutron. So for the most part, a proton is about the same mass as a neutron. So electrons have a much smaller mass than a proton or neutron. So the mass of an atom is generally considered to be equal to the sum of the protons and the neutrons in an atom. So protons plus neutrons equal the atomic mass, or A, in AMU. So Rutherford postulated that there was a very small, dense nucleus that contains protons and neutrons, with the electrons around the outside of the atom, and that most of the volume is empty space. So if the nucleus was 10 to the minus fourth angstroms, okay, which is a size unit, then the whole volume of the atom would be, or the rather the diameter would be 1 to 5 angstroms in diameter. So what's the mass of an element that has 10 protons and 11 neutrons? Well, protons plus neutrons, 10 plus 11 equals 21. That's what the answer is. How many neutrons are present in an oxygen atom with a mass of 18? That would have to be 10 because oxygen's atomic number is 8. 18 minus 8? Yeah, or 8 minus 18, rather. 8 from 18 is 10. Yes. How many protons are present in an atom with a mass of 13 AMU? If it has 7 neutrons, it has to be 6. What's the mass of an element with 18 protons, 18 electrons, and 22 neutrons? 22 plus 18. 18 protons, 22 neutrons. That would have to be 40. So, how we name these things, and we're going to stop with after this. The number of protons in the nucleus is what we call the atomic number. We use Z to designate the atomic number. The number is given for each element on the periodic table, and it's usually right above the chemical symbol. Okay, that's the Z number, or the atomic number, or the number of protons. Now, we call protons and neutrons, because they're found in the nucleus, we call them nucleons. So the number of nucleons in a nucleus is what we call the mass number. And we use the term A, or the letter A, to designate the mass number. So to get the number of neutrons, okay, it's pretty simple. The A, or the mass number, minus the Z, or the atomic number, equals neutrons. Now, a couple ways we write these, right? There are two common ways to write them. Method one is X, and X would be the chemical symbol for the periodic table, dash the A number, or the mass number. Another way is the A, or the mass number, is a superscript, and the subscript would be the Z, or the atomic number. X would be the chemical symbol. So we would write silver 107 as AG-107. 107 is the A, or the mass number. We could also express it like this: 107 AG 47. 47 would be the Z, or the atomic number. 107 would be the A, or the mass number. AG would be the symbol. We'd have to look up strontium. We'll work these tomorrow. Now here, this is sodium. It actually gives me what it is. 23 would be the A, 11 is the Z, or the atomic number. What would be the mass number? It would have to be 23. How many protons? Well, it's got 11, because that's the Z, or the atomic number. How many electrons? Well, it's 11, because electrons in a neutral atom is equal to the number of protons. So it's got 11. How many neutrons? Well, A minus Z, 23 minus 11 would give me 12. So it has 12 neutrons. We will practice this. How many neutrons does this element have? Well, 80 minus 35. That would be 45. We'll come back. We'll work a bunch of these tomorrow. So we're going to end here, okay? And I will try and do this, the next video on isotopes, okay? And other than that, guys, we're going to have a great Monday. Talk to you later. Coach Scott, out.